She did her undergraduate education at the universities of Notre Dame and Lebanese University in Lebanon before moving to France for her PhD, where she did a PhD in physics at the University of Montpellier. Then she came to the US, where she was a postdoctoral fellow at MIT for 3 years. And just last year, she moved to the University of Florida in Gainesville to become an assistant professor there in the astronomy department. And today she will tell us about the architecture of stars. So take it away whenever you're ready.
Thank you so much. Can you hear me well? I think I am frozen, but I am here. I don't know why.
We can hear you and see you. Yes.
Okay, perfect. So I will go ahead and share my screen. Right, so can you all see my screen okay?
Yes, looks good.
Okay, perfect. So hi, everyone. Thank you so much for the invitation to give a colloquium. I'm very happy to be talking to you all about my research and my talk entitled Stellar Archaeology, Digging into the Chemical and Physical Properties of the Oldest Stars. I just want to see that I'm not a very big Google Hangout user, so I cannot see you if you have any questions. I cannot see you if you raise your hand, but please feel free to interrupt me and ask your questions if you have along the way. So I am both an observer and theorist of stars, and while many of you are very much solar enthusiasts, I am a stellar enthusiast. I like to study stars, and I use them to answer questions about the origins, particularly origins of the chemical elements. And understanding the chemical elements is very important for us to understand how our galaxy, how our universe got to evolve until its present day, and how our beloved star, the sun, got to have all its beautiful elements that we observe in it today. And so for those who are not very familiar with the term stellar archaeology, maybe I can give you a bit of a refresher. So you might have heard of the term archaeology, which is here on Earth, meant to explain how we search for and study the oldest fossils by digging underground to find anything that we can left over from the older generations or older cultures in order to understand the history of Earth. In stellar archaeology, we do the same thing. We don't get to dig in the dirt, but we get to dig into the vast universe and the vast Milky Way in order to search for and study the oldest stars. And we use them to try to understand the history of the Milky Way and the history of the chemical elements that we see and we observe today in present day in the universe. And as you can imagine, my talk is going to be a lot about stellar archaeology, so I'm going to talk about old objects. And so in order to do that, I have to take you all the way back to get started to the origin or to the beginning. And we have to go back in this story all the way to the Big Bang, because it all started with a Big Bang. Now, this story is very nice and interesting. I always love telling it because chemically, and please note that this is not what the diagram that you're seeing is not to scale here. If we look at a cosmic timeline, right after the Big Bang, the universe was made merely of a few elements, mainly hydrogen, helium, a little bit of lithium, boron, and beryllium. There was nothing else in the universe at that time. A few million years later, the universe got to form its very first stars that we call population 3 stars. These stars were formed from that gas that was only hydrogen and helium. And because these stars are believed to be massive, they must have exploded a long time or shortly right after the birth by the first supernova explosions in the universe. Now, what's very interesting about the first stars is that at their cores, they got to forge the very first heavier elements in the universe. And by heavier, I mean anything that is heavier than carbon. And so at the end of their lives, these first stars exploded as supernova explosions and ejected the very first chemical elements into the universe. After a while, the second population of stars got to form a few 100 million years after that. And these population 2 stars, or the second generation of stars, what was interesting about them is that they had low mass. And so therefore, they must be present until the present day. They must be surviving until the present day. And so the chemical evolution throughout the formation of second and third and fourth generation of stars continued. And throughout the cosmic recycling of chemical elements, heavier and heavier elements got to form until the present day, where we have our stars, we have our exoplanet systems, and we have our sun, which is a direct product of millions and billions of years of chemical evolution. Now, when I'm trying to answer questions about the early universe and I'm trying to understand the origin of the chemical elements, I have to study the oldest stars there is. And unfortunately, I cannot study the first stars because we believe that these are long dead today. But however, I can study the next best thing, and that is the population 2 stars. Luckily, because they are low mass, as I said, they are still around. And so these are the type of stars I'm going to be talking about for the rest of my talk. And luckily, we get to find them sometimes in our cosmic background. And so, as I said, the properties of the first stars, what we know from cosmological simulations, because we cannot observe them, we know that they must have formed in what we call dark matter mini halos. And these are mini halos that are found around our galaxy today that are dark matter dominated. We believe that they were very, very massive because we don't have any observational evidence of the presence of these first stars today. And we'll believe that they are short-lived. That means they only survived for a couple million years and are no longer around. One thing we know about them, though, is that they must have ended their lives with energetic supernova explosions, and they were contributed majorly to the reionization of the universe, which is very important. And so in order for us to study these first stars, we cannot do it directly. We have to do it indirectly. And this is where stellar archaeology comes into place. So stellar archaeology is looking for the low mass remnants or fossils of the early universe that we do find in our galaxy today. And we use the largest telescopes that we can find in order to infer the properties of the star-forming cloud from which they were formed, believing that this star-forming cloud must have been enriched by a first star. And so, where do we find these oldest stars, these population 2 stars that we can use for stellar archaeology? While they are rare, we do find them often in the Milky Way halo, in the halo of our Milky Way. We find them in the field, we find them in globular clusters, and we find them in dwarf galaxies. And you can see here an example of a cartoon of our galaxy that most of these stars can be found in the extended halo. However, the problem is that most of these stars are too far and too faint to be detected. And so in order for us to find the best candidates in order to do stellar archaeology with, we have to do several vetting procedures and several vetting steps until we find the best candidates to go through. Luckily, many of these stars, and you can recognize here a stellar spectrum of multiple what we call population 2 stars from the collected from the Sky Mapper survey in Australia. Many of these stars, while they don't have a lot of absorption lines because they are old and at the time there wasn't enough metals to have a lot of absorption lines, they have very strong calcium H and K lines. So even the oldest one of them and the most metal poor, and I'll explain what metal poor is in a minute, they have very strong H and K lines. And so we use this H and K line to get a first guess or first estimate of the iron content in these stars. Once we find really good candidates, we then follow them up with high resolution spectroscopy with bigger telescopes. Therefore, the fundamental tools of my research is using observational data from both optical and UV telescopes, preferably the biggest one around, because the bigger, the higher the resolution, in order to follow up stars that are believed to be chemically interesting and believed to be old. I then go to these telescopes, collect the spectra that you can see here of an example of one old star, which shows some but not a lot of lines. And then I compare these spectra with models, particularly radiative transfer models that include line strengths, atomic data, radiative transfer, and stellar atmospheric models, in order to infer the chemical compositions of the oldest stars. And so to give you a refresher, these population 2 stars are called metal poor stars, or for those in the audience that don't know much about metal poor stars, why do we call them metal poor? As we said before, at the early universe, and even today, most stars are made mainly from hydrogen and helium. Many of them have about 73% hydrogen and 25% helium. However, as you know from our beloved periodic table, we have many, many more elements in there. However, astronomers didn't like the current periodic table, and so they decided to change it. They decided to call everything else that is not hydrogen and helium metals, or Z. And so the idea here is that all the stars that have very few of these metals are believed to be old because at the time the universe didn't have enough time to form these metals, and so we call them metal poor. However, stars that are younger, where the universe has had more time to produce many more of these heavy elements, we call them metal rich. For example, our sun, which has, as you know, solar values, everything is referenced to the sun, is a metal rich star as compared to the stars that I'm talking about earlier, which are metal poor. And so in my research, I try to find these metal poor stars because it means that they are old. Now, not all metal poor stars are created equal. In fact, we have created a bunch of nomenclature in order to allow us to divide them into subcategories. Now, the reason why we divide them into subcategories will be more clear in a minute when I explain it. However, we basically divide the metal poor star based on their iron content or total metallicity, Fe/H. And this ranges between stars that are regularly metal poor, which usually denotes Fe/H less than 1. We also have very metal poor stars, extremely metal poor stars, as we have less and less iron, ultra metal poor, all the way to ridiculously metal poor stars, which have a metallicity of -10. Of course, we have not found any ridiculously metal poor stars yet. However, interestingly, in the past few years, with the use of really targeted photometric surveys that are looking really deep into the Milky Way halo, we have been lucky to find some stars that are mega metal poor, which means that their iron to hydrogen abundance is less than -6. And I was lucky and happy to be part of some of this work and some of this discovery. And so, what is the difference between these different nomenclatures and why should we care? If I want to study and place constraints on the first stars or the early universe, I need my stars to have undergone only a few enrichment processes. I cannot have a star that has had a lot of pollution or a lot of enrichment. And so therefore we can divide these stars or these metal poor stars by the likelihood of them having either a single progenitor regime, so only a single first star would be their host or their progenitor star. We call them mono-enriched. Or stars that are less metal poor, those are likely to have more than a single progenitor regime. And in this case, we call them multi-enriched. And so, as you can imagine, the stars that I am most interested in order to constrain the properties of the first stars have to be mono-enriched and not multi-enriched, preferably. And so for the rest of my talk, I'm going to tell you how I use these tools, which are the oldest metal poor stars, in order to constrain the physical and the chemical properties of the oldest stars. Particularly, I'm going to highlight how I use these very old iron poor stars or metal poor stars to constrain stellar atmospheres because they are extreme, as you can imagine. And I'm going to highlight how I also use them in order to understand and highlight the chemical enrichment of the early universe and what do they allow us to learn about this early universe. I'm going to start from the stellar atmosphere's point of view. Now, as I said, I study the chemical compositions of stars by comparing their spectra that I collect from large telescopes to models of radiative transfer code. However, one thing that you might have heard before is stellar abundances. We measure stellar abundances, we measure solar abundances. The thing is that we don't really measure abundances. Abundances are only as good as their radiative transfer models. And in order to make our radiative transfer models simpler and nicer, we adopt a lot of approximations. Some of them are okay, and they usually don't affect our chemical abundances. However, many of them are not. So some of the approximations that we usually adopt and should not really affect the chemical compositions of stars are assuming plane parallel versus a spherical model, assuming that the atmosphere is homogeneous, it's stationary, it's in hydrostatic equilibrium. However, one of the other assumptions that is very commonly assumed in solar and in stellar abundances and chemical composition studies is local thermodynamic equilibrium and adopting one-dimensional model atmospheres. These can highly affect the chemical compositions of stars, and I will aim to highlight in the next few slides why it is important for us not to ignore such approximations when we model our stars and our sun. And so just for those in the audience who don't know much about the topic, what is local thermodynamic equilibrium, or LTE? From now on, I will call it LTE. So in LTE, we usually assume that the matter in stars is assumed to be in equilibrium with the radiation field over a finite volume in gas, which means that over a small volume of the gas, we assume that collisions dominate over radiation. And in this case, this is what drives the local properties of the gas to be in LTE, or local thermodynamic equilibrium. And what a nice consequence of this is that we can assume that the properties of the gas will be defined by a single temperature at each depth inside the atmosphere of the star. On the other hand, non-LTE assumes that the photons that we are observing in terms of spectral lines carry non-local information. And this means that if I'm observing an absorption line in the spectrum of a star, it must have been affected by lots of other radiative and collisional interactions from other transitions between the single atom itself and other atoms. And so Martin Asplund says that very nicely in his review in 2005, non-LTE is where everything depends on everything everywhere else. And so based on this, we can imagine that one thing to solve when we're doing non-LTE is we have to take into account all different transitions that can take place in a single atom. So to show you a further example on this, when I'm studying an atom in LTE, if I want to study a single line or a single absorption, all I need to care about is the lower and upper level and the properties of a single line transition. However, if I'm doing this in non-LTE, and here I'm showing you an example of my iron model atom, and this is only iron 1, we need to take into account about 80,000 transitions, and this is only iron 1. And what you're seeing here in this lower diagram is energy of different atomic levels that are found in the iron atom. Now, yes, it's true, you cannot see this very details, and I apologize for that, but there was no way I was able to plot this by showing the details just because the number of atomic levels that iron atoms can have. Now, this obviously complicates our computations. However, what I want to show you in the next few slides, that it's actually important for us not to ignore non-LTE in calculations because it can highly affect our results. One way that we can quantify the effect of ignoring non-LTE, or rather what we call the non-LTE effects in stars or stellar atmospheres, is by introducing what we call the departure coefficient, which is defined as the level population densities in non-LTE divided by the level population densities in LTE of a single transition or a single level. And what I'm showing you here is an example of the departure coefficients on the y-axis as a function of optical depth. And you can see that the high optical depth, this introduces the core of the star. And as we go toward lower optical depth, we're obviously heading to the outer parts of the atmosphere of the star. And you can see that in the line-forming region, where lines form in stars and in the sun, which is mainly between -4 and -2, many stars, or all stars, including our sun, which has a solar abundance or solar metallicity, can have a lot of departures from LTE or have a lot of non-LTE effects. What you notice thus, though, is that as we go toward lower metallicities, which you see here in the two blue lines or the two blue curves for much lower metallicity stars, that the deviations from LTE increase much strongly and much severely toward lower metallicity stars. And this is why these stars are very important or are very strategic for us to use in order to constrain our models of non-LTE. Now, what are the effects of ignoring non-LTE in stars? We usually use stellar abundances, particularly abundances of iron, in order to derive the basic stellar parameters of stars, including the effective temperature, the surface gravity, the microturbulent velocity, and the metallicity of the star. And what I'm showing you here is the deviation on the y-axis for each of these parameters from LTE. So you have non-LTE minus LTE. And what I'm showing also in red here are the standard uncertainties that we usually derive for stars, and everything is color-coded per metallicity. What you can see is that the deviations from LTE for the temperature, for the gravity, for the metallicity is larger, or actually much larger in cases than the usual uncertainties we derive for these stars. And so therefore, neglecting the non-LTE effects in deriving the basic parameters of any stellar population can highly affect our conclusions. And in fact, sometimes we can derive wrong conclusions about stars. In addition to that, not only for stellar parameters, as you know, for aging stars and determining the mass of stars, one very common method is using isochrones in order to compare the gravity and temperatures of stars to theoretical models. Now, as you can imagine, because this is a theoretical model, it is usually calculated in LTE. However, if we do include non-LTE, we found that there would be a phenomena called isochrone climbing, where the real parameters of the star in non-LTE as compared to LTE moves the star upward on the isochrone, and therefore means that we can probably derive, or we will end up deriving, wrong ages and wrong masses from the stars if we ignore the non-LTE effects. Now, you might tell me that, this is a lot of calculations, and if I want to include non-LTE, I'm probably have to do these calculations, these heavy calculations, and I don't really want to do that. Well, so to give you a little bit of an example, we tried to come up with a relation of an estimated non-LTE effects on stars as a function of metallicity in 2017, where we studied some of the oldest stars, or some of the most metal-poor stars we can find between -4 and -8 in metallicity that you're seeing here on the x-axis. And we derived the non-LTE correction defined here by delta, iron over He. And we found that it obeys more or less a linear trend. And so one idea is that if you are interested to estimate your non-LTE effects, particularly for iron, without doing the full calculations, you can actually use this calibration or this calibration method in order to determine this as a function of your LTE metallicity. Interestingly, what we found is that this method applies even well to stars that we did not force this relation. And so here you can see that less metal-poor benchmark stars, we tried to put it on this scale, and we found that it matches very well this calibration equation, and so it is valid to use for most stars. Now, one other thing that we can provide is my group here at UF is very interested in finding solutions and providing software for people to estimate the stellar parameters and metallicities in non-LTE for those who don't want to do the full calculations. And with my graduate student, Yang, who is currently at UF, we have developed an automized code with a web interface that will be published soon, that allows you to derive your stellar parameters and abundances in non-LTE. It uses a very robust and multivariate interpolation module because at the end of the day, the different parameters, gravity, temperature, metallicity, they're all interdependent. And so previous models have only used interpolations in a single regime. We are using multivariate interpolation modules and slice sampling MCMC fitting in order to fit to observations and derive non-LTE stellar parameters. First results can be seen here and have been very exciting. We compared the temperature, the gravity of benchmark stars and stars that have non-spectroscopic parameters to our details or to our results. And we find that indeed, you can see here in the shaded areas, for many of the benchmark stars that you see on the x-axis, we see that the results are very, very interesting and very promising. Our uncertainties are very small and match very well those that are of parameters that have been determined non-spectroscopically. But more excitingly, they actually match well parameters that are determined from Kepler asteroseismology. And as you know, asteroseismology is one of the most accurate ways to determine stellar parameters because they are more or less model independent. And so we're very excited about these results, and hopefully we'll be publishing this code soon to be used. We also plan to add 3D effects to these models in the future, in the near future. And so one thing that you might ask is, okay, you've been showing iron all the way now. What about other elements? Can they also be suffering from non-LTE effects? And how does that vary as a function of metallicity? A very interesting review paper in 2014 by Maria Bergerman collected the non-LTE or the typical non-LTE effects that can affect different elements that you see here on the x-axis for a number of benchmark stars, including the Sun and Procyon. And as you can see that for different elements, the non-LTE effects are different and can range all the way from 0 all the way to 0.6 or 0.7 dex, which cannot be ignored if you're really interested in accuracy in very detailed abundances. Moreover, this is very important and have been shown recently that star-exoplanet chemical correlations are also very important and require a certain level of accuracy. And so if we want to take that into account to better understand the exoplanets, we need to take non-LTE effects into account for all elements or as much elements as possible, not only for metal-poor stars, but also for solar-type stars. One final thing I would like to show you about the non-LTE effects and why it works is because ideally we would expect physical properties of the stars to emerge without forcing it. And so this is one little exercise we did in 2019 where we compared the abundances derived from calcium-1 lines and calcium-2 for a number of stars that are mainly metal poor over extending a range of temperatures. And what we find is, and what we expect, from these two ionization levels or abundances derived from these two ionization levels is to give zero discrepancy. There is no reason why abundances from calcium-1 and calcium-2 should be different. However, we can see that in LTE, the dispersion is quite large between these abundances, whereas the non-LTE models naturally and organically produce a very small discrepancy between the models, which shows that non-LTE in fact works, and we can use metal-poor stars in order to test these models and improve upon them as much as possible. One final thing I want to say about these spectroscopic models and non-LTE is that we need as many atoms as we can get, and we need to perform these calculations for a number of atoms, as I showed you before. I am leading one of these projects here in the US, where I have already developed a number of atoms that I have grids of non-LTE corrections for. And so if you're interested, please feel free to talk to me afterward or email me. I also have a number of atoms in the work that are strategically and chemically interesting that have never been looked at before, that I'm currently building and also interested to look into their non-LTE effects. But I want to say that if you also have any interest in any of the other elements, please also feel free to talk to me. I am taking orders at the moment. So I'm going to switch gear here, but I'm going to take a minute to ask if anyone has any questions about what I've been talking about so far.
Rana, I've got a quick question that might be relevant for this beginning part. Well, you mentioned the population 3 stars, the earliest stars are, I think you mentioned they're exclusively massive. What would have prevented smaller stars from forming that might live longer?
Yeah, that's a very good question. And one of the reasons that theoretical models predict is the lack of cooling agents in the molecular clouds, such as carbon and silicon, that would usually fragment large molecular clouds to form smaller atoms. And so we believe that because the first stars, or the gas from which first stars were formed, didn't have any cooling agents, the stars that is formed must be more massive.
Okay, thank you.
Yeah. Any other questions? All right, if not, I will continue, and I'm happy to take more questions at the end, of course. So now I'm going to switch gears, and I've talked a lot about how I use metal-poor stars in order to constrain stellar atmospheres, particularly in adopting or constraining models of non-LTE. I'm going to talk now about how I use metal-poor stars with my collaborators in order to constrain the chemical enrichment of the early universe and how we can use them to better understand this enrichment. And so one of the questions that I'm interested to answer with metal-poor stars, as I said earlier, is the properties of the first stars. What were their masses, as someone just asked? What were their supernova explosions like? What were their energies? And what were the mechanisms, particularly, by which these supernova explosions took place? And again, one motivation to answer these questions is because, as I said, these first stars were responsible to re-ionize the universe. And so our understanding of these energies and mechanisms can help us a lot understanding the early formation of galaxies. So some of the different theoretical suggestions for supernova explosions of first stars include the usual core collapse spherical supernova explosions. Because they were massive, some people suggest that maybe they must have exploded with with jets that would release a lot of energy, or pair instability supernova explosions, which we have not been able yet to answer or to observationally confirm to date. Now, you might tell me, okay, well, what about cosmological simulations? Maybe these can help you answer some of these questions. Unfortunately, cosmological simulations show us a range of masses that range all the way from 0 to 1,000 solar mass for the first stars. And this here, I'm just presenting a small illustration by Tilman Hartwig, who kind of compiled all the different studies that have been done in the past decade on masses derived for the first stars. And so what I'm trying to say is that from a theoretical point of view, we're not really converging anywhere on the masses of first stars. However, there's another way that we can do this. We can use stellar archaeology in order to invertly or backwardly build up the population or build up the IMF of the first stars. How do we do this? We, as I said earlier, we try to find the very oldest stars that have or likely to have a single progenitor first star or single first star as a progenitor. And then we measure or study its chemical compositions, as you can see here in the top right and left panels, where I'm showing the chemical compositions in red squares for two hypermetal-poor stars. So both of these stars have a metallicity below -5. And then we compare these compositions to first star supernova explosion models at different masses and at different energies. And then the best fit, we use different techniques for fitting these observations in order to estimate the the masses of the first stars as well as their supernova explosion energies. And doing that, we've been able to build up some kind of IMF that you see here on the bottom left, and also the energy range of their supernova explosions. We find that many of the first stars have masses ranging between 10 and 30 solar masses and have energies that are relatively faint, on the fainter size, about 0.6 times 10 to the power 5 Earth. However, what you see missing here in both of these upper plots that I'm showing is that we don't have a lot of heavy elements. Obviously, in order to use this method to constrain the supernova explosion yields, we need to obtain a large number of chemical elements in these stars. However, because they are faint and because they are metal poor, they don't usually show a lot of these elements. Some of these elements, however, that are unique, such as zinc, nickel, chromium, can be found in Hubble or can be found in the UV. And therefore, in 2019, we were able to use Hubble in order to determine the first ever detection of the element zinc in a hypermetal poor star. This was very, very interesting at the time because this would be the first detection of such an element in a star that is that metal poor. And from that, we were very interested and very surprised, or not very surprised, as I'll show you in a minute, to find that the zinc that we measured in this star is highly enhanced relative to iron. This is not very, at the time, it didn't make very sense because zinc is an element that is nucleosynthetically explosive. It is formed during the supernova explosion. So what would be the mechanism of the explosion that would allow zinc to be that enhanced in a second generation star? As I said, this is not very surprising. At the time, it was a little bit, but in fact, when we look at the trend of zinc to iron abundances in metal poor stars, as we go toward older stars, we have an increasing trend. This has been an open question for a while in the literature of how would zinc be produced as such in the universe, especially in the old universe, and why do we see such an increasing zinc trend as a function of metallicity? We were able to do some investigation and work with people doing supernova explosions of first stars, and we deduced that the only way to actually produce zinc at such amounts that we observed in this star, and to also confirm the evidence that I showed you before, is if the first stars would explode with highly energetic supernova explosions that have jets. And the goal of these jets would be to extract the elements that are forming during the supernova explosion, such as zinc, onto these jets out into the interstellar medium from which our star, our second generation star would be formed. Now, this was very exciting because this has been alluded to in theory, but has never been observationally shown before. But what was more interesting is the implication of such a supernova explosion. We have a lot of spread in the chemical compositions of the early universe stars. In fact, many of our population 2 stars show a lot of dispersion in the chemical compositions. Particularly, many of them, and you might have heard this term before, are called carbon enhanced metal poor. They have a lot of carbon that we're not able to explain. And so by showing such a very energetic explosion that can happen in the early universe, we might be able to show that there might have been more than one formation channel or enrichment channel taking place at the early universe. Because if these first stars that are formed in these small mini halos would have a supernova explosion that had jets, it would have the ability to emit the jets into a neighboring mini halo from which a second generation star such as ours would have formed. And so this will have a lot of implications for our understanding of the chemical enrichment and as well as metal mixing in the early universe. And in fact, since this study, there has been a number of cosmological simulations and studies that have looked at possible what we call external enrichment or ex situ enrichment in the early universe, and found that this is a very likely scenario for why we see multiple populations of abundances in the early universe. And this is very exciting to us. Now, in order to talk to you about something other than zinc, I'm also very interested in nucleosynthesis of other elements, particularly those that lie at the bottom end of the periodic table. Now, just to give you a refresher, I'm sure you all know this, but many of the elements are forged at the cores of the stars, particularly those all the way to iron, where at the end of its life, usually massive stars are not able to fuse anything heavier than iron, and so it will end its life as a supernova explosion. But what about the elements that are heavier than iron that are found in the periodic table? What about those such as gold or such as uranium? Where are these formed if not inside the stars? It has been shown that all the way since Burbage, Fowler, and Hoyle put out their amazing paper on nucleosynthesis of stars, that there's another process taking place that forms these heavier elements called the neutron capture process, where the idea is that we would have a seed nucleus that would be bombarded by a large flux of neutrons that would build up the formation of heavier elements and heavier isotopes. And since many of these isotopes would be unstable, as you can see here in the chart of nuclei, it will then beta decay into a lower element and then build up heavier elements, so forth. However, it has been shown that we need two types of neutron capture processes to account for all the elements we observe in the universe and in stars. We need a slow neutron capture process, and the term slow means that we have a slow flux. And this has been solved for a long time. We know that this happens mainly during the stellar evolution of massive stars, such as AGB stars. But we have another method that should account for the formation of even heavier elements, such as gold, such as europium and uranium. This is called the rapid neutron capture. Up until the present day, and by present day, I literally mean 2 years ago, we had no idea, or we have not been able to constrain the site of the rapid neutron capture process, or as we call it, the R process. Where does it take place? Where is it possible for us to find a neutron flux so fast and so heavy to bombard a seed nucleus to form these heavier elements? Some sites that have been suggested include neutron star mergers, or binary stars that merge together. The reason for that is, well, if you need a neutron source, there you have it. You have two fully big grown neutron stars that would merge together, coalesce, and it will release a huge flux of neutrons that can possibly form the R process elements that we see in the universe. However, up until 2017, we have never been able to observationally confirm this. We had never observed neutron stars that are merging. But luckily, in 2017, LIGO and Virgo were able to observationally confirm the first gravitational wave due to binary neutron star merging. But what was interesting to us is not just the gravitational wave. Of course, that was very exciting. To us, it was the electromagnetic counterpart that came after the neutron star merger, and as we call it, a kilonova. Observers and scientists around the world all pointed their telescopes toward this event and saw what we call a kilonova, or a light curve of a kilonova, which is an event that happens or forms because of decay or radioactive decay of the formation of heavy elements such as the R process. And you can see here that there are two components to the kilonova, one that is red that lasted for a few days, whereas we also saw a blue part which lasted only for a few days, as in 1 or 2, whereas the other lasted for 20 days. This electromagnetic kilonova confirmed for the first time that the R process that forms the lanthanides and the actinides that we observe in the universe can indeed happen in neutron star merger, but also confirmed that it's the dominant side of it. However, what's the problem? If I want to study the R process elements from a kilonova, I cannot directly do that, even though the media alluded to. The media told us that during this event, a lot of gold was formed. Every single media was saying that gold is formed during that event. And that is true. However, if I want to observe gold, I cannot do it during the event itself because this is a very energetic and high-speed event. The lines would be blurred. I can use the metal poor stars or the old stars to study the R process like I did it for the first stars. Why? Because the R process is a universal event. It's a universal, unique event. What you are seeing here is the abundance on the y-axis as a function of atomic number for a metal poor star that is called CS22892 that is studied first by Chris Sneeden in 2008 in Texas. And what he found is when he compared the R process in this metal poor to the solar or the scaled solar R process abundance, he found an incredible match to all the R process elements. This is not a match the numbers to each other or match the blue to the red. This is not done by forcing. This is actually just amazingly, what we discovered that the R process elements that we find in our sun today were produced by the same event that must have produced the R process in the old days, in the old stars. However, unfortunately, we cannot use the sun to study the R process because it has been polluted over a very long time. But I can use the old stars that have not been polluted, that are used as fossils, in order to understand the R process. And this is why we decided to form, I'm a core member of a collaboration called the R Process Alliance, which is as cool as it sounds, where we are a multi-stage, multi-year effort to provide observational, theoretical, and experimental constraints on the nature of the R process to try to understand it. So we go out to the telescopes and try to find lots of stars that are enhanced in the R process. As you can see here, pardon me, in the example for HE 1523, which is a star that is highly enhanced in our process as compared to the other HD 122, which is not. And you can see that those that are enhanced in the R process would show a lot of strong lines. And so what have we found so far? In the past few years, we have been able to increase the rate or the number of our process stars that show lots of enhancement just in the last few years by more than doubling. And right now, honestly, it's been tripling the numbers of our process. Before, it was very funny because in Simbad, when you would look at old R process stars, they would be specified as peculiar stars. People did not care about them, but right now we know that they are very, very significant. Now, to kind of finish this up, I also want to say that it's not enough that we only look at these R process stars or at stars in general in the optical, because we, as I showed before, there are many elements that we can only observe in the UV. And in fact, what we find is that the UV observations allow us to increase the number of elements that we can observe in star by about 34%. And in last year, we were able to obtain HST observations for an R process metal poor star that has evidence of showing about 93 elements in the same star. And this is the first time that we're able to study the full R process elements that we can find in the universe in a single star, which is very exciting. And it's work that I'm doing with my graduate students. And so we are expected to find a lot of exciting things. So what I would like to tell you is that the UV is very important, and I really appreciate the work that you are doing here at HAO for, I know, to support UV studies for the sun and hopefully also for other stars. So to conclude, I just want to say that I am a stellar archaeologist. My tools are the metal poor stars. I use them to constrain stellar abundances, stellar atmospheres, using high observation studies, and I use models. I use them also to constrain models of the first stars and first chemical enrichment in the universe. And I hope that the universe keeps giving us more and more of these beautiful fossil stars that allow us to learn a lot about the universe. And with that, I leave you with my summary takeaway points, and I'm happy to take any questions. Thank you so much.
Thank you very much, Rana. Do we have any questions? Ricky?
Yeah. Hi, Rana. It's me again.
Hey, Ricky.
You got the. You were mentioning the importance of aspherical supernovae for the enhancement of zinc. I'm wondering, what are the mechanisms that cause, such a aspherical explosion, and what sort of parameters would determine the likelihood of such a state? That seems like a thing that would really complicate your models for chemical enrichment if it's something that can happen sometimes but not all the time and so forth.
Yeah, no, that's a good question. And yes, definitely it would complicate models because you cannot model an aspherical explosion with 1D, albeit, let alone 2D. You need a 3D model. And right now, supernova explosion models are still working on trying to improve this. However, it is very much needed, and it has been alluded to, as I said earlier in the literature, that we see a lot of discrepancy in the abundances of these elements. And I only showed zinc, but I want to tell you that nickel, chromium, everything else of these iron peak elements show an increasing trend toward lower metallicity. We simply cannot explain this with spherical models. Now, there was also another allusion to why aspherical supernova would be more dominant in the early universe, is because these massive, or these first stars, were very massive, right? We've established that, but they were also very fast rotators. And one other idea is that they would be also responsible for the GRBs that we would have observed from this, so the very high energetic events that we observe in the universe. We see that at lower metallicities, right? We always link GRB observations for high energetic supernova taking place in external galaxies, but we cannot do that. We have not done that for the first stars because we were missing this observation link. And so we were hoping that this kind of observation link, that we were able to observe such an element in a hypermetal poor star, which must have come from a first star progenitor, would be our proof that these types of supernova explosions can take place.
Thanks. So that's sort of interesting and ties it back to things that HAO is interested in, I guess. If the early universe is full of only very massive stars, they don't have the convective zones that make nice magnetic fields like we're so interested in, and therefore there's no braking, and therefore they are fast rotators, which could possibly explain the asymmetries in the type of supernovae that they undergo. That's really cool.
Yeah, thank you.
Thanks.
I agree.
Do we have any other questions? All right, well, if not, then thank you again for a nice talk, and we'll conclude here.
Thank you so much, Paul. Again, thank you for the invitation, and I was happy to give a talk. Very nice meeting you all.
Thank you.
Actually, I did have a question. I pressed the wrong button.
Ah, okay. On you go, Phil.
Sorry, yeah. This is Phil. I really enjoyed the talk. It's so refreshing to see very interesting basic astrophysical processes being tied together across the age of the universe using what most astronomers consider to be the most boring thing you can do, which is spectroscopy. But anyway, I had a couple of questions. One is, of course, these very heavy elements you mentioned towards the end. How well known are the basic atomic transition probabilities that you need to build abundances, and are they coming from measurements, I presume, or because calculations would be very, very difficult for these singly ionized and neutral massive elements?
Yeah, that's a good question. We, as you can imagine, Phil, we have a lot of gaps in there that we're trying to fill in terms of atomic physics. So laboratory-wise, we have some well-known transitions that we were able to measure. However, this is using the R process itself is not really easily reproduced in the lab. And so I am, as I said, the R Process Alliance is also meant to experimentally answer questions about the R process. So we are collaborating with AFRIB, which is the Facility for Rare Isotopes, which is headquartered at Michigan State University. If you don't know about it, it's going to be one of the fastest accelerators, or they have the fastest accelerator going online in 2022 in the US or North America. And they're going to be able for the first time to measure R process elements and atomic data for R process elements, especially the heavier ones. So for example, I can give you some examples for elements that are very interesting to us, like thorium and uranium. We use them to determine age of the star because these elements decay on cosmological timescales. However, we don't have a lot of atomic data for them. And so AFRIB is going to be able to answer some of these questions, hopefully soon.
Yeah, and I just had one more question. When you have such low metallicity stars, say the population 2, extremely low metallicity, to what extent is their internal structure different? Because the onset of convection is going to be very, very different. And so I was just wondering to what extent the interior stellar models might affect the surface conditions or may not. I mean, is there Are they well understood, the interiors of these very, very low metallicity stars? I suppose they are.
So the interior part, I believe, is not that different or not that discrepant from more metal-rich stars. I would say the atmospheres are still not very well understood, and not just what I talked about today in terms of non-LTE. As you can imagine, that these stars are very convective, as you said, and so they would be suffering also a lot from 3D effects. And I did not talk about this today because I have not started looking into this in depth, but it's something that I'm very interested to start doing. At least some studies in Germany and in Australia have found that the 3D effects can be quite as large as the non-LTE. Not the dominant. The non-LTE is still dominant because you have radiation overcoming the collision. However, 3D effects are very important. And so it's very important that we look into this with 3D models. But I think that there's more work to be done there.
And finally, I was reminded of one thing that you put up there, which is you didn't spend time commenting on, but you put it in, so I feel I should ask.
Sure.
The origins of sort of habitable worlds as a function of the metallicity. To what extent do you think, while clearly habitable worlds are in the well-mixed multiple exposure regime like we are, is it likely to find habitable worlds in globular clusters like population 2 stars or something, or is it just totally unlikely? I have not thought about it.
Yeah, so it's the dream, right? I am no exoplanet expert myself. However, my study of the topic and talking to people doing exoplanet studies is that it's a little bit more difficult. And that's for a number of reasons, is because you need metals in order, again, to fragment your disks to form worlds to start with, let alone habitable worlds. And so right now, I believe in exoplanet studies and observations, the cutoff is about -1 metallicity. Some people have been able to push it to -1.5, but I don't think there's been any worlds or any exoplanets so far determined or found in this very metal poor regime. I know that there are some particular exoplanetiers that are looking into globular clusters to try to find that. It's not going to be obvious into finding the exoplanet itself, but we might be able to find signatures of exoplanets in the star. And so, for example, to give you, lithium is one of the elements that is believed to signal a planetary engulfment. And we find this in many metal poor stars. In fact, I didn't show this, but my student and I are working on a -2.5 star that shows the highest lithium observed to date in a star. And we're not able to justify this by stellar evolution models. So we believe there must be some external conditions happening, including possibly the engulfment of a previous planet. So it's very exciting.
Fascinating. Thank you.
Yeah.
So we have one more question in the chat from Turing. Do you want to ask yourself, or I can read it out if you prefer? Okay, so he's asking, you were able to get an idea of the mass of these population 3 stars using the metal poor stars. Is it possible to investigate the proportion of binaries among the population 3 stars using similar techniques?
Yes, ideally we would probably do the same technique where we would compare nucleosynthesis models of multiple stars to observations of population 2 stars, like we did for our star. However, the binarity itself would have not as strong, let's say, signals that we would expect to find in these stars. So binarity could, for example, lead to carbon enhancement or exchange of carbon and oxygen. And this has been proposed as one of the reasons why we see these carbon enhanced metal poor stars. But it would, for the first stars, we don't believe there has been a lot of carbon production, or at least it should be subtle. So it might be a little bit more difficult. I know that some studies are trying to use the galactic or stellar archaeology to infer binarity or understand binarity as well. So yeah, to answer your question, I think ideally we can, but we haven't made a lot of progress there yet.
Okay, thank you. And if there's no more questions this time, maybe we can conclude for the second time. Or does Ricky want to say
I'll
something?
make you go for a third. This is,
Go ahead, Ricky.
I love the use of adjectives in astrophysics. Is the ridiculously metal poor the official technical term that's used through the literature? And would the overwhelmingly large telescope be the ideal instrument for looking at ridiculously metal poor stars?
Yes, exactly. So it's a literature. I did not come up with it. It was in the review literature by Anna Frebel in 2018. She came up with this terminology. We ran out of exaggerations to add, and so I guess that's appropriate. And yes, actually, Ricky, you're right. The overwhelmingly large telescope, or the OWL, I think, will be used, or suggested to be used, to study immediately the first stars. However, the bad news is that if you've seen the paper, they suggest that they should build it on the moon for us to be able to get any signal from first stars. A paper by Anna, I'm sorry, I forgot the last name. So it's gonna take us a while. We need to first worry about our ground telescopes until we really go to the moon. But it's very exciting nonetheless.
Great, thank you.
Yeah.
Okay.
Thanks.
Thank you again.
Yeah, thank you very much, everyone. Nice meeting you.
All right.
See you all later. Bye-bye.
Bye.